next speaker is Ms. Santos from Hanover, who will be telling us about dynamics and localization in polar lattice gases.
So, thanks a lot. First of all, I would like to thank the organizers. Pleasure to be here. So, today I would like to tell you something about dynamics in polar lattice gases, and you will see why I was asking the question I was asking before, right? Also concerning the issue of localization in absence or any presence. So as we saw already in the previous presentation, and I knew that we were going to introduce it in a fantastic way, so I will just skip many details. So the physical dipolar gases has attracted since several years a lot of interest due to the new physics introduced by the that interaction. The flow rates and isotropic in the case of magnetic dipoles, and the case of electric dipoles as well, like polar magnetic later So this new physics appears in different contexts. There has been a lot of activity in the recent years in the issue of supersolidity, for example, in physical dipolar boson 6. There will be talks about that. I will not mention this too much. In recent years, we have been working quite a lot on this. Many of the work together with Francesca Ferlaino and Tom Blanc, who is here, and who is also here. Other people of Institute is here, sorry. But we have been also addressing issues like vortices, and then I will be talking about that, about their very nice recent works on this. And also recently on the experiments. But as I say, I will not talk on this. I will actually focus more on the dynamics in optical lattice. So in the very similar setup that was mentioned before in the next topic. So I consider the dipolar particles in an optical lattice trapped in the tight binding regime. And I will consider actually two different types of models that can be studied in this. One is the model that was discussed before, the Hubbard model. So where you have the particles tunnel, they interact on sides. So this is the case of the both Hubbard model. And they may have, and this is a new ingredient, of course, strong interside to the nearest neighbor, to the next nearest neighbors, and so on. Actually, in many most of the talk I will just consider hardcore version, so the limit of very large U, I think is case of experiments here. And also I will mostly focus in this version, which is the case like 1/resistance with about 3, also I will discuss this a little bit more at the end. So as we were mentioning before, there was some similar experiments of Francesca on this, and of course we have seen the financial cost. The second type of models that I would like to discuss are spin models, in which the particles are spins, so they are not mobile anymore, but you can have non-trivial dynamics due to the internal degree of freedom. So this may be because you take molecules and you encode them in rotational states, or you have bilayer systems, so you may have atoms, magnetic atoms. Actually, some of the initial pioneering experiments in DS, but a group of rural works and dealt with, for example, with chromium, with actually with a spin-off setup, so with more than 2 levels. And later on, we will also experiment with Francesca. So here you have X-Y coupling and mediated by dipolar interaction, and eventually also easy like that. So actually, you have also the possibility to have models with tunable power laws here. So let's just 1/r to the power 3, like for example with trapped ions, which was being implemented already. But I will mention this only very tangentially in the talk. I will mostly concentrate in the case that we have the dipolar interaction. So let's start with the case of spin systems. So now we have particles, for example, polar molecules that is this seminal paper that we do in GLA. And now these particles cannot move, these molecules cannot move, but I can encode the spin in two rotational states. Now we see the 1 right? And so now if I have two neighboring molecules, spin up and spin down, they can flip-flop, and so they undergo this exchange with mediated by the dipole. So I say, I think you can molecule, but you can have many other systems, you can have similar systems. So I would like to discuss, first of all, to illustrate the possible physics that new physics, or interesting physics that you can have in this system with recent work that we did with Maria. And then I will go to three different types of disorder scenarios where you can have this interesting disorder physics in the system. So the setup that I have in mind here is actually a setup which has been implemented already in GLAM, at least partially. So you have two layers, and you are able to prepare the upper layer in one spin state and the rotation state, and the lower layer in the other state. So you have the red layer and the blue layer. And now due to Riemann-Dipole interaction, you can flip-flop, and you can get a blue defect in the red layer and a red defect in the blue layer. And now once you have created it, this guy can move now by flip-flops. So you have interlayer creation of this type of defects and intralayer motion of these defects by both of them mediated by the dipole interaction. So this is this type of Hamiltonian. You have this type of flip-flops within the layers, and you have this motion within the layers. And you may have also easy exchange here. You have, for example, horizon. So actually, you can map this problem to hardcore versions. This transformation, and then you get this. You get a model which you get basically the creation of defects. So basically, you're already moving into the momentum space. What you get is this type of intralayer box and the correlated interlayer creation. And the dispersion of this band here is given by the dipole interaction set. So here you are inheriting
what is the feeling of each layer?
Sorry?
What is the feeling of each layer?
The feeling.
The feeling.
I will come to this because the feeling is surprisingly robust. I will comment on that in a second. So now you get this correlated interlayer pair creation. Can we also dependent on it's given by the dipole. And now what happens in this system is that the vacuum of this system, so basically the system in which you don't have defects, basically all red or blue, is unstable against pair creation. So you get instability of the vacuum, and you get the pair creation in this model, in other models of unstable vacuums. And what you get is actually that due to the properties of the dipole interaction, you get the formation of correlated pairs. So you get, you can recognize here, this is this type of squeezing like component. And you get the formation of correlated pairs with K and minus K of these defects. And this is this can be controlled by orienting, for example, the dipoles with respect to the normal of the plane, or by playing with the Ising term, which I did not include here. You get patterns in the formation of the structure factor. So you get different patterns in the structure factor, which you can control the topology of these patterns by playing with the orientation of the dipole. Now, and this coming up to this issue of the disorder. Now, what happens if you have empty places? Here, this is actually the situation in the experiment. Three experiments in Princeton, or I think a few factors are 15%, if I'm not wrong, something like that. And so now what happens if you have these entities? Now, what happens is that the effect is surprisingly robust. It survives even in rather sparsely filled lattices. So this is the filling factor, 90%, 70%, 30%, 10%, and still you see these patterns. Yes. So this is a surprisingly robust phenomenon. Now, this issue of removing molecules from the layer brings me now to the first of the disorder scenarios that let's discuss here, which is the incomplete distinct lattice. Yes. So the situation is now similar. Now I have just one layer, But well, first of all, I can have a three-dimensional system, and I will discuss this in a second. But I have the situation in which this layer is imperfect, this lattice is imperfectly filled. The particles cannot move, so I have now these particles here which cannot move. But I have this, all of them are down, and I put one of them up. Yes. So now I can forget about the rest. Yes, and this behaves like a hardcore Gaussian, as I was mentioned to you. So basically, what I have is the propagation of particles in this type of random graph. Since the interactions and this exchange depends on position or not on orientation, this means that I am getting this type of peculiar random, peculiar disorder here, in which the filling factor acts as an effective disorder. So now, this is a problem that we studied some years ago with Jordan, Boris, and Shalom. And basically, what happens in the system depends very much on dimensionality, like I mentioned before. So, for example, if you are in a two-dimensional setup, right, then what happens is the following. So basically, this picture is encoding some information. So this is the spectrum, the states, the lattice filling, and this number of here is characterizing the level spacing system. So basically, red means ergodic states, blue means localized states. So this is basically a quantifier of the character of the estimate. And here you see that the low lattice filling, you have that these states are basically localized, all the spectrum is localized. But then, starting with a sufficiently large lattice filling, you undergo the system undergoes this type of localization to the local system. Yes. There is also, actually, this is pretty much given by the finite size of the system, right? But for any practical finite sizes like 100 times 100 or something like that, this filling, this critical filling would be around half a billion. Now, in three dimensions, the situation is very different because in three dimensions, what you have is a different family of states. Other states which are neither localized nor ergodic. It's something in between. So what is in terms of the non-ergodic extended states, which have a multifractal character. So basically, what you have is typically a localized state is a state that if you make your system bigger, it does not grow because it's localized. An ergodic state is a state that you make the system twice bigger, it gets twice bigger, right? And this type of system of states are states in which you make your system twice bigger, but it does not get twice bigger, it gets less than that. Right? So this is this will actually dominate this type of multifractal state will dominate steam transport at low lattice filling. How this happens in the actual setup and how this happens in time is something that could be quite interesting to study in the next. So this is the first scenario that I would like to discuss. The second scenario involves the quasi-disorder. So this is the famous O'Brienbre model. You have primary lattice and secondary lattice. And this secondary red lattice is incommensurate, has a field which is incommensurate with the first one. You have nearest neighbor hops, yes. And so this is the hopping, and this is the quasi-disordered strength. Now, due to the so-called self-duality of this problem, right, in space and dimensional space, you have no mobility edges actually. So you have that all single particle states are ergodic, and beyond a given threshold here, to here is delta of T, you get that all single particle states become localized. Now, if you have long-range hops, which in the language of spin is the long versus change, you expect self-duality is violated, and then you expect the appearance of mobility edges. So this is a problem that we studied some time ago, and here you see basically the phase diagram. This is the quasi-disordered strength, and this is the power of the change. We analyze the general power, but as I say, this is 3 for the dipole-dipole interaction. Infinity would be the nearest neighbor box, right? And sure enough, if you go to infinity, you have this transition at exactly 2 because all ergodic into all localized. But for 3, you see the appearance of these regions here, in which the system actually has mobility edges, but it's rather peculiar because what you have is that due to the fractal structure of the spectrum, the famous Hofstadter butterfly, you have you get like sequential transitions, like part of your spectrum becomes localized, and the next part of the spectrum becomes localized. You get that the different subbands becomes localized for different values of this delta of the T. Yes, and you have a rather sizable here window at least.
What are those different colors?
These different colors is just this region where you have this this is localized, right? These are the ones that the next branch.
P1, P2, P. What are
This is just that this situation in which all the states between the so this is between 0 and 100% of the states are ergodic. Then all between 0 and this beta percent, so to say, are ergodic, and the rest is localized. This is yellow. The next one is green, and so on. So this is in what concerns single particle excitation, so that is a huge excitation. But what happens if you have many of these excitations? If you have many of these excitations, then this problem will become a problem. By the way, I did not mention, for example, how could you get this, for example, in the context of molecules, for example. In principle, one could think in playing with the differential polarizability of the different speed states and trying to use something. Then, if instead of using this type of quasi-periodic modulation, you get now a truly, for example, specular, something like that, then you can induce basically anchor, or as good as it gets, uncorrelated disorder. But now you will have, say, many of these excitations, say 50 will happen now. This becomes a problem of MPL, many of the localization, which has been addressed by a lot of people actually. But let me just mention one issue, which is that if you have a look now to the states as a function of disorder and as a function of power, the other interaction, so 3 again is the type of interaction, then you get this the localization to manual localization. But what is interesting in the manual localizing this system is that contrary to the short range systems, here due to the fact that the locally localized motion are not exponentially but rather algebraically localized, you get that the entanglement network, for example, grows algebraically and not exponentially. Now, what is funny, this is the only point that I would like to comment here, is in this work that we do this together with the group of readers below, we showed that this power here seems to be actually rather universal. Just so we had a look to this power as a function of the power of the change and disorder at this edge for different models, like the XY model, the XST model, and the standard Hubbard model, and we show always the same power in the entanglement space. It's really interesting to see what happens with other measures of entanglement, which are easier to measure. So we see that spin models open a lot of interesting possibilities in what concerns disorder and what concerns the creation of entanglements. Now let me move to the second type of systems that I would like to discuss here, which are the extended Hubbard models. Yeah, so the models that were discussed in the previous one. So again, we have open, we have in principle on-site interactions, and we have this nearest neighbor, next to the neighbor, and so on. So now the question that I would like to address here is how is the particle dynamics in a disorder-free polar lattice? So now I don't have disorder. Yeah. So, but what happens with the dynamics in this system? How easy or how difficult is it going to be? And here I will make several simplifications in most of the talk. I will first of all consider a hardcore boson, so I will remove this excess at the very end. And I will mostly concentrate in one-dimensional systems, so I will say also something about 2D at some point. And I consider that this behaves like 1 over j to the power 1 over distance to the power 3, but I will also like to revisit this at some point in the book. So, in order to see that which kind of funny dynamics one can have in this problem, let's go to the very simple case of 2 particles. So I have 2 particles which are sitting next to each other. I create them like this. So this is dynamical problem, right? It's not a thermodynamic problem, it's a dynamical problem. I create them together, and then I can have a physics which is very similar to the physics of the so-called repulsive results. So what I have here is that if the interaction between them is much larger than the bandwidth, then if I try to break this pair, I have to accommodate this entity somewhere, and this somewhere will be in the gap. So this means that I will not be able to break this. And as a matter of fact, the form is a dynamically bound time. Now, as for the case of the particle compares, these dimers can still move, but in second order with the dimer. Now, this is, as I say, basically the same as for the particle compares, which are created on site, so they move like this. Right? But in the case of dipoles, we have something else, which is well illustrated if you consider two of these dimers. Because now these dimers are interacting via the dipolar tail. So, and the dimer hopping competes with the dipolar tail. So now, if this guy tries to move inwards or outwards, right, you will change the energy of the pair. And if the change of the energy of the pair is, again, much larger than this dimer hopping, not that the pair hopping, then this forms a cluster, yes, with a dimer of dimers. Yes, and this happens for a sufficiently critical length, the factor of D over T. So dimers get bound fixed distance, and actually with this will lead to a sort of quasi-localization. So if I create a dimer gas, right, and this dimer is sufficiently close to each other, right, and if this range of V of T is sufficiently large, it doesn't need to be very close, right? So that need to be a very high density to be pretty sparsely filled. And the system will clot, basically because of this formation of dimer clusters. Yeah. So this is the first indication that we have here that motion can be complicated. In particular for these particular types of states, right? I will generalize it for other states. Now, the dimers can have a funny physics in this type of near stable dimers can have funny physics, and this is best illustrated in the case of a two-dimensional lattice, because it is indeed the case that these dimers are not seeing the same lattice as the single particles. It is true for any two-dimensional system, but this is particularly true in a triangular lattice, particularly interesting if you want in a triangular lattice. And here you can see why. If you take now these circles are the triangular lattice, and you have these dimers, and these dimers are moving. So now this guy moves here, so the dipole is perpendicular, and this is an equilateral triangle. So if this guy moves here, it's a complete resonance motion. But now the center of mass moves here. If this guy moves here, the center of mass moves there. If you follow the motion of the center of mass is actually following a Kagome lattice and not a triangular lattice. And a Kagome lattice is characterized by the appearance of a flat band, right, which is not completely flat because of second order processes here. But what this means is that if you start with the diamond and analyze the expansion of this diamond in the lattice, then you see a bimodal distribution. You see that part of it is projected into this dispersive bands and part is projected into the flat band, and sometimes you get two different velocities. And indeed, this can lead again to quasi-localization of this flat band. Now, you see that these particular states, there are particular states which are particularly prone to localization, right? There is also the possibility that you form a sort of mega cluster. So now we have been talking about dimers, but in principle, it will start with a bunch of particles together, right? And I can ask myself the following question. If I put these particles together with two end caps and I liberate the end caps, like in the experiment, for example, in manual expansion analysis, do these particles move or do they remain self-bound? And the surprising thing is that they remain self-bound even for precisely low values of V over T, some things which could be available nowadays, for example, in the average experiment, right? So something of the order of 2.5, it would be already self-bound. And this is also as a ground state. So say for if V is more considered, this would be the ground state as it has been studied by the Barcelona proposal. So you see that the motion of particles due to the interplay between tunneling and interstate interaction can become rather complicated. And this brings me now to the issue of many body localization without disorder. So because it becomes now more or less clear that even very few conserved quantities may result in non-ergodic dynamics. So something like MDL or MDL-like in this system, you have because of construction, but because you have some emergent dynamical constraints in the problem, which fragment your field space. And this has been actually explored recently in the context of the star localization of the lattices. There have been several experiments. For example, this one is the group of Monica. So now, what does this have to do with our problem? So let's consider the most minimalistic model of all that contains localization, which is this hardcore system in one dimension with just nearest neighbor interaction. We will see later on that the tail actually plays a very important role. But let's consider just for the moment the case which you have nearest neighbor interaction. Now, if I just have nearest neighbor interaction and I increase this ratio between B and T, which is the right figure of merit that we have been seeing already many times, so the ratio between nearest neighbor interaction and coping. Now what happens is that this number here becomes a conserved quantity. Yes, so you have the emerging and emerging dynamical constraint. So if B over P is much less than 1, this becomes a conserved quantity. So this means that now you have to split your system into states which have different number of nearest neighbors, and basically you don't mix them. And this leads to the fragmentation of the Hilbert space. So basically you get blocks, right, of states with the same number of nearest neighbors, but it's more than that, because there are states which have the same number of nearest neighbors, but which you cannot connect dynamically, because in order to connect from this state to that state, you will have to go out of this family. Because the hopping is what it is, yeah, and the hopping will break this bonds. So basically, you can illustrate this fragmentation by having a look to, for example, how focus states may be written in the basis of eigenstates, or vice versa. And so these are focus states, and these are many value states ordered in such a way that you can see these blocks structure. So here I am plotting this amplitude. And you see that if now you are in this block here, yes, basically here this is not completely zero, but it's very, very small. So what it means is that these states will become basically de facto only connected with each other, even in a very, 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 very yes. Now, in the case of just nearest neighbor interactions, what happens is that if you increase this V, right, this just simply strengthen and strengthen and strengthen this dynamical constraint. For example, if you are concerned already this constraint, increasing V further does not play any role. So it's saturated. But if you have the tail of the diagonal interaction, then what happens is that increasing this V actually increases the role, of course, of next steps in the current, in particular, the next to nearest neighbor interaction, so basically interaction to two neighbors. And this is enough. Yes, you don't need much larger interaction to basically close your system. And this is, you can see already from here, because now you see that the focus states in the basis of eigenstates become basically a diagonal. So this means that your focus states become eigenstates of the problem. So as a matter of fact, what this means is that it doesn't matter which state you throw in the system, yes, it will become basically stopped. Right? It will become a stationary state or close to be a stationary state. So, and actually, if one has a look to this, what people call the shattering of the Hilbert space, so basically now it becomes massively fragmented. Now you can see, doing some analysis which I will not enter, you can see that this should occur for something like D or D of one. And actually, you can see this, for example, if you study the inhomogeneity, so which is very similar to, for example, how Immanuel Bloch has been studying the many localization. So, so you start with the initial focus state, and you ask yourself, is it going to become homogeneous? There's some way of measuring this. And then what I show you here is basically this is the nearest neighbor, this is D over T, this is this inhomogeneity parameter, right? And this is the nearest neighbor, and this is the case with 1 over r to the power 3. Once you surpass this Hilbert space shattering, basically this 1 over r to the power 3 becomes much more inhomogeneous than the homogeneous case. And then the nearest neighbor case, and the nearest neighbor case is very saturated here, as you can see, because of this that I told you that increasing D does not matter anymore. Very funny enough, if you go to low values of U over T, the tail actually helps to the delocalization because actually it helps to bridge energy gaps, energy difference. So, and how many minutes I have there? 5 minutes.
Yeah.
Okay. So in the last idea, so let me just mention a couple of things. First of all, how good is this approximation that the tail is of the form of 1 over distance to the power 3? Well, this depends actually on the problem, right? And this is just some details that I would like to give now. So if because this depends on the shape of the Wagner function. So now I am considering a one-dimensional problem, and I am constructing this one-dimensional problem in different ways. I can, for example, take a three-dimensional lattice and isolate basically by one row by filling the tunneling in the other two directions. But in order to do that, they need to have a strong lattice in the other two directions, which means that they have to compress very strongly the one you find. And as a matter of fact, these transversal directions, these two directions, become very compressed in comparison to this axial direction. And when you do the math, basically you see that the 1 over r to the power 3 is actually not a bad approximation. It's not exact, but it's not a bad. But if what you do is to take a transversal confinement, which is here, for example, a harmonic confinement, then you can get into the regime in which this is actually larger than 1, not smaller. And when this happens, the tail of the dipole interaction is not anymore of the form 1 over r to the power 3, right? You get, for example, this is the 1 over r to the power 3. This is the dj over d. So this ratio is the ratio between next to nearest neighbor and nearest neighbor interaction, which is actually the important thing that I told you before, right? The important thing is the ratio between next to nearest neighbor and nearest neighbor interaction. Yeah, and this may be sizably different, right? So, and actually you can parameterize this with an effective exponent here, yeah, which I mean, typically we have assumed that this is of the order of 3, but it is actually maybe actually sizably different. For example, in this particular case, is 2. This depends, let's say, universally actually on the transversal confinement. There's a lot of universal. Now, this is important because what this makes, without entering into what it is, we have no time, is that the system actually, in what concerns dynamics, instead of behaving like a system with interactions became like 1 over r to the power 3, it becomes like a system with interactions became like this power. Because it does not matter so much what is the interaction to the nearest ones in what concerns dynamics, because the important thing is the nearest neighbor and the next nearest neighbor. And that's it. This has also consequences for the statics of the impact that we discussed. And now let me finally move to this issue that I was moving through, see what happens when you have soft core. Because if you have soft core, there is something that I did not mention yet, because it was not so important for hardcore, which is this term here. Yeah, which plays a very important role, as you will see, in the case in which the lattices are not very deep. And this is the so-called dipole-assisted hopping. In the dipole-assisted hopping, you have this, so you have this hopping mediated by the density here, and this prefactor here actually happens to be negative, has a different opposite sign than this one. So in order to see why this is important, let's just make a very simple calculation here. So I take this bare hopping, I take the dipole-assisted hopping, I sum the two of them, and I do something very brutal. So I will do a mean field treatment. So I will just simply take this density as like twice the density. And then you see that instead of having that my hopping is t, now I have sort of effective hopping, which is t minus this one. This depends on density and depends on this number here. And this number here happens to be proportional to b. So this means that when I increase b, I am increasing also this number. And now let's see. If the important thing is now that these t effective are not t, the important figure of merit is not b over t, but b over t effective. But now, when I make b over t bigger and bigger and bigger, I'm not making this number smaller and smaller and smaller. Sorry, bigger and bigger and bigger. So I'm not making my system more and more and more and more non-ergodic, as I was going to do before. But it happens that I am getting this b over t now in both places, in the numerator and in the denominator. So basically, when b over t becomes very large, I get a constant. And this constant depends actually on the lattice step. If this constant is below this shattering that I was commenting to you, basically what happens is that my system, even if I increase b over t a lot, due to this activation induced by this dipole-assisted hopping, will still be delocalized. And actually, this is what happens. This is this inhomogeneity that I was commenting to you before. Now, without this dipole-assisted hopping, you will expect that if the system becomes largely inhomogeneous, so that is non-ergodic, whereas with the dipole-assisted hopping, it will become basically delocalized. But as I say, it depends on the lattice depth. If the lattice depth becomes very large, then this dipole-assisted hopping becomes less and less relevant, and eventually you recover this. This is the total. Okay, so with this, I am finished. So we have seen this manifestations that you can have in this SP model and in the Hubbard model, and then we finish by taking the people with whom I have the pleasure to collaborate in English and CS. Thank you very much. Okay,
we have time for a few questions. Have you discussed fragmentation and higher dimensions, two dimensions.
We did not have a look to this point.
So, great thought, thanks. I was wondering in the case of the 1D system, as we've shown in our experiments, we have a lot of disorder. So just thinking experimentally, how we would, just think about localization.
Yeah.
Coming from the natural extremes compared to our experiments.
So in principle, there is an interplay between this interaction-induced disorder and this dipolar-induced quench disorder that you have. So basically, what will happen is that so what I'm saying here is that if your interaction is sufficiently large, right, then the critical disorder to observe localization basically goes to zero. Now, if your d over t is smaller, then there is a critical value of disorder at which this appears. Yes, and actually in one of the papers we have a figure like this, having also some analysis, for example, in the context of nearest neighbor models by Bartlett, who has been studying this.
So, I'm concerning the safety situation, like having a fixed number of, like the number of nearest neighbors as a constraint in the model. I would just scare if you have to plan for problems, right? Like that would depend on like how strong it is.
If you have a drive, right?
Like a swapping.
This difficult to say because this will change basically the rules of the game now, right? So I will have to think about it. But because you have in mind more like reverse systems.
For example.
This will change the rules of the game because now you will not disturb the.
Exactly.
Any other questions? No? Okay, so we have a coffee break until 10.